มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้าวิทยาลัยเพื่อการค้นคว้าระดับรากฐานสถาบันสำนักเรียนท่าโพประกาศจัดตั้งขึ้นเมื่อวันที่ 14 มีนาคม พุทธศักราช 2554 รับรองสถานะโดยสภามหาวิทยาลัยนเรศวรให้สถาบันสำนักเรียนท่าโพสำหรับฟิสิกส์ทฤษฎีและจักรวาลวิทยาหรือ TPTP ซึ่งแต่เดิมนั้นดำเนินการภายใต้จิตอาสาของเหล่าคณาจารย์ฟิสิกส์มาสเตอร์ทพาเอียนตั้งแต่แรกเริ่มเมื่อวันที่ 8 สิงหาคม พุทธศักราช 2539 ต่อเนื่องยาวนานจนเป็นสถาบันแห่งการผลิตผลงานศึกษาวิจัยและเป็นอาสมบ่มเพาะนิสิตสาขาวิชาฟิสิกส์ทฤษฎีให้มีความรู้ความเข้มแข็งทางวิชาการจนได้รับการยกสถานะให้เป็นหน่วยงานระดับคณะวิชาอย่างเป็นทางการถือเป็นการประกาศเจตนารมณ์ผลักดันยุทธศาสตร์พิเศษของมหาวิทยาลัยนเรศวรที่จะก้าวเป็นมหาวิทยาลัยวิจัยชั้นนำของประเทศในระยะเวลา 10 ปีที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตผลงานต่างๆมากมายผลงานวิจัยตีพิมพ์ระดับนานาชาติจำนวน 125 บทความผลงานวิจัยตีพิมพ์ระดับชาติจำนวน 8 บทความงานประชุมวิชาการระดับนานาชาติจำนวน 7 ครั้งงานประชุมวิชาการระดับชาติจำนวน 10 ครั้งการจัดอบรมเชิงวิชาการระยะสั้นและโครงการบริการวิชาการจำนวน 58 โครงการการจัดสัมมนาวิชาการ 200 ครั้งคณาจารย์ของวิทยาลัยได้รับรางวัลเชิดชูเกียรติทางวิชาการจำนวน 15 รางวัลบันทึกข้อตกลงความร่วมมือกับสถาบันชั้นนำอื่นๆจำนวน 13 สถาบันหนังสือและตำราวิชาการจำนวน 13 เล่มวิดีโอสอนออนไลน์ผ่าน IF Channel จำนวน 34 วิดีโอนอกจากนี้ 10 Plus Consortium ได้สร้างเครือข่ายความร่วมมือทางวิชาการระหว่างสถาบันฟิสิกส์กว่า 20 สถาบันกลุ่มเครือข่ายพิษณุโลกฟิสิกส์เน็ตเวิร์กได้ส่งเสริมกิจกรรมสัมมนาวิชาการในจังหวัดพิษณุโลกและสถานีฟิสิกส์ศึกษาคือการให้ความสำคัญกับครูผู้สอนฟิสิกส์ในโรงเรียนระดับมัธยมศึกษาให้เข้มแข็งและถ่ายทอดสู่นักเรียนผู้เป็นอนาคตของประเทศที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตบัณฑิตสำเร็จการศึกษาในหลักสูตรวิทยาศาสตร์มหาบัณฑิตจำนวน 8 คนหลักสูตรประกาศนียบัตรบัณฑิตชั้นสูงจำนวน 10 คนหลักสูตรปรัชญาดุษฎีบัณฑิตจำนวน 5 คนผลงานเหล่านี้จะสำเร็จขึ้นมาไม่ได้หากปราศจากผู้สนับสนุนและแหล่งทุนวิจัยอาทิมหาวิทยาลัยนเรศวรสำนักงานกองทุนสนับสนุนการวิจัยสกว.สำนักงานการวิจัยแห่งชาติวช.โครงการปริญญาเอกกาญจนาภิเษกคปก. นิวตันฟันศูนย์ความเป็นเลิศด้านฟิสิกส์เทพสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมูลนิธิโทเรเพื่อการส่งเสริมวิทยาศาสตร์ The Abdus Salam International Center for Theoretical Physics ICTP อื่นๆปัจจุบันวิทยาลัยเพื่อการค้นคว้าระดับรากฐานมีคณาจารย์ทั้งหมด 9 ท่าน โดยแบ่งเป็นคณะผู้บริหารวิทยาลัย 4 ท่าน 3 ห้องปฏิบัติการวิจัย ห้องปฏิบัติการวิจัยจักรวาลวิทยาและความโน้มถ่วง ห้องปฏิบัติการวิจัยทฤษฎีสนามควอนตัมและฟิสิกส์พลังงานสูง หน่วยวิจัยฟิสิกส์ดาราศาสตร์และจักรวาลวิทยาเชิงคำนวณ จากอดีตถึงปัจจุบันเรายังคงดำเนินการภายใต้พันธกิจสำคัญอย่างต่อเนื่องดังประกาศเจตนารมณ์ท่าโพณวันที่ 8 สิงหาคม พุทธศักราช 2539 เราจะสร้างโรงเรียนฟิสิกส์ที่ดีที่สุดแห่งหนึ่งของประเทศขึ้นที่นี่ โดยหวังเป็นอย่างยิ่งที่จะส่งเสริมสังคมแห่งการเรียนรู้จุดประกายเยาวชนและสร้างบุคลากรให้มีความเข้าใจลึกซึ้งเห็นถึงความสำคัญของวิทยาศาสตร์พื้นฐานต่อยอดวิทยาการความรู้ด้านต่างๆให้ก้าวหน้าบนรากฐานที่มั่นคงทางวิทยาศาสตร์ซึ่งเป็นกลไกสำคัญให้ประเทศไทยขับเคลื่อนไปอยู่ในระดับแนวหน้าของโลกในอนาคต
Okay, and good afternoon, everyone, and welcome to EVE Colloquium Online Seminar Series number 10, organized by the Institute for Fundamental Study, Naleson University, Thailand. My name is Sikalin Yukong. I am EVE Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. Let me first give you the idea why we need to do this kind of activity. Most of the time, academic conversation would normally circulate among the scientists, yet it's bridging the gap between the science world and the general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and enjoy in progress of the advanced research. For this talk, we have Matt Vermeerend from Loughborough University, United Kingdom, to give a talk on a topic, evolutional principle for integrable systems. Let me spend a bit more time to introduce our speaker formally. Matt completed his bachelor degree in mathematics with minor in physics from KU Leuven, Belgium. And then he went for his master and PhD in mathematics at Technology University Berlin, Germany. Currently he holds a doctoral prize fellow at Department of Mathematical Science, Loughborough University, United Kingdom. And His research interest is definitely integrable systems. The talk would be lovely 40 minutes long. Before I start, during the talk, if you have questions, you can put them in the comment. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give this skin to our speaker, Matt. Skin it your nose.
Thank you very much for that introduction, and thank you for having me. Good afternoon, everybody, or good morning here in the UK. So my talk indeed will be about integrable systems, and the other word in my title is a variational principle. You may be more or less familiar with either of those terms, so I'll try to give a good introduction. So most of the first part of my talk, of the first section, will be an introduction to these integrable systems. And I'll briefly also mention what the variational principle is. So this is refers to the calculus of variations as in Lagrangian mechanics. And then in the later parts of my talk, I will combine these two ideas. So integrable systems, I should already say, are usually differential equations. So I will both give a Lagrangian description of ordinary differential equations and then later on partial differential equations. And then, of course, I'll talk a bit about why we do this and what the connections are of this variational perspective to more textbook approaches to integrable systems. So let's start, as I said, with an introduction to integrable systems. The way to intuitively understand integrable systems, at least in my opinion, is to think about what differential equations are and how they behave when they are linear and nonlinear. So linear differential equations are usually the first one we learn about in courses on differential equations. And they are, well, relatively easy once you get to know them, because you can always solve them and they have very useful properties. Like you often have traveling wave solutions, but what you always have is this superposition principle, meaning that if you find one solution and a second solution, then their sum will again be a solution. Or if you have a solution and you rescale it, then you will again have a solution. So linear differential equations are nice to work with, have some very predictable behavior. Unfortunately, a lot of our world is described by nonlinear equations. And they are, well, many of them are chaotic, which has a precise mathematical meaning, but the intuition should be clear. So nonlinear equations are often chaotic, have very complicated behavior, could be impossible to solve, in general, very difficult to understand. And the integrable systems, they are kind of the exception to this nonlinear case. They are not linear equations, they are nonlinear, but they have some structure that makes them nice, that still makes them show a lot of these good properties we have in linear differential equations. And in the introduction, or before the introduction, when the live stream was waiting, we had this very nice background, this animation of the water waves based off this Japanese print. And that was a very rough sea. It would be quite chaotic, disorganized. So that would be a good example of this nonlinear situation. But you can also have water waves that are integrable. And I have a little video that shows you a very nice example of this. So this is it's in a lab setting, but it's a narrow and quite shallow canal. And then the water on the right here will be released, and it forms a nice traveling wave. So similar to the linear equation, we see here a traveling wave solution. But this one will actually be a nonlinear one. This is a very famous example of an integrable wave equation, or a soliton equation. Soliton is a name for such a solitary wave. And in this video, well, we can't really see all the details that are relevant. We see one traveling wave, so we could be tricked into thinking it is linear. But if we would have the same wave but higher, in the linear equation, that would still be a solution. But here, the higher wave would have to travel more quickly to still be a solution. And if we have several waves and look at their interaction, we will see more clearly that it's almost a superposition, but not quite. And I have never seen a good video of this with water waves, but we can make a plot of this. So this is the space-time plane. The horizontal lines are space, and the darker the color, the higher the wave in this position is. So the time starts on top, and here we have one big wave, and then a smaller wave, and an even smaller wave. And because their velocity, due to the nonlinear aspect of this equation, their velocity depends on the size, the larger one will travel more quickly. So as time progresses, as we move down on the slides, the larger one will catch up with the smaller ones. And if this was a linear equation, they would just pass through each other and be momentarily one very big wave and then the same three waves again. Now, this is almost the same thing, but not quite. We see the same three waves coming out, but what they do in the middle, what they meet, is quite complicated. This is not just a superposition, this is really, again, a nonlinear effect. And what we can also see, they come out in almost the same way, but they're not exactly in the place where we would expect them to be. You can see this most clearly for the smallest wave. It jumps quite a way back in this interaction. So the same waves come out, but with a bit of a phase shift, as we say. So it's not in exactly the same position where it would be if it was a linear interaction. So I hope this gives you a little bit of an intuition on this one example of shallow waves in the canal, which is modeled by the Korteweg-de Vries equation. It shows you that the behavior is almost as good as you would wish for, almost linear, but there are these nonlinear aspects. And if I go back one slide, that's the equation here, this nonlinearity here. So you have the subscripts denote derivatives. So you have the time derivative equals a third space derivative plus a product of the wave function and its derivative. And it's this product here that is the nonlinearity that causes the equation not to be exactly linear. And whenever you see such a nonlinear term in an equation, you expect the worst, but in this case, it only changes minor things, so there is some hidden structure in this equation that makes it integrable, that makes it behave very close to linear. So this was kind of the behavioral side. What about the mathematical side? As I said already, most nonlinear differential equations, so far I've shown you wave equation, but the same is true for ordinary differential equations. Most of nonlinear differential equations are actually impossible to solve exactly. The examples we see in our lectures on differential equations are, in a sense, special cases because they can be solved. And the integrable systems are the exception. They behave nicely, but also we can solve them, or at least find some special solutions usually. So they have some kind of underlying structure that helps us find the solution and make sure that they behave so nicely. And there are different mathematical approaches to understanding these hidden structures, but a very important one, and the main one I will think about in my talk, is that an equation will be integrable if it has many symmetries. And this will get a bit more precise when we see some examples, but you're thinking about continuous symmetries here. So not mirror symmetry, which is on or off, but for example, translational symmetry, which you can do infinitesimally, or rotational symmetry, things like that. It can also be much more difficult to visualize, but always something that has some continuous parameter. And since it has this continuous parameter, you can take it in its infinitesimal form, which really means that every symmetry is just another differential equation. For example, a translation in the x direction would be the time derivative equal to minus the x derivative. So if we translate in our mind from symmetries to differential equations, then the statement becomes that an equation is integrable if it is part of a large family of compatible differential equations, the equation we start with and its symmetries. But then we have this word compatible that we have to make sense of. And again, there are a few mathematical interpretations you could give to it, But the most basic way of viewing this is usually done in terms of Hamiltonian mechanics. And if you remember, the title of my talk, Variational Principles, refers to Lagrangian mechanics. And so Hamiltonian and Lagrangian mechanics are kind of opposite sides of the same coin. So we'll start at the Hamiltonian side and later on move on to the Lagrangian sides. Because the Hamiltonian side is really where in the textbooks the integrable systems would be formulated. So let me give you, as a refresher or a quick introduction, the basic setup of Hamiltonian mechanics. The idea is that your full dynamics is encoded by a single function, a function mathematically on a cotangent bundle that really, for our purposes, is just a 2n-dimensional Euclidean space where you have q's, which are position coordinates, and p's, which are momentum coordinates. So we have n positions qi and n momenta pi. And then this one function determines the dynamics of our system through these equations. So the time derivative of a q coordinate is given by the partial derivative of the Hamiltonian with respect to the p coordinate, and the other way around with a minus sign. And this has some nice mathematical consequences. If you know about symplectic structures, this flow preserves some symplectic structures, so it's some abstract geometry. And much more relevant, or much more immediate to practice is that it preserves the Hamiltonian. And indeed, usually the Hamiltonian will be the total energy, so you would expect this to be preserved. This is just a mathematical consequence of this framework. So indeed, if we take the Hamiltonian to be a kinetic energy of some particle with momentum p in a potential u, the potential should be v, and then we get from these two equations, they become this, that the velocity relates to the momentum, and the change in momentum is the partial derivative of the potential. So if you combine that, we just get Newton's law with the conservative force given by this potential v. So the acceleration times the mass is minus the gradient of the potential. So that's kind of the standard case of the Hamiltonian mechanics, but you can generalize this quite a bit. You can also work with other types of functions. But this is a good starting point to keep in mind. We will need one different view on the same thing. Is instead of using these two equations here, we can write the same thing using a Poisson bracket. And at first, this just seems like introducing a bunch of notation, but it will be a very powerful tool. So the Poisson brackets of two functions of this cotangent bundle, which are just functions of positions and momenta, is given by this expression here. So you combine a partial derivative of f with respect to momentum, multiply it with partial derivative of g with respect to position, minus the other way around, and that you sum for each component. Now, why do we define the bracket that way? It's because of this definition. If you plug into the brackets in the first slot the Hamiltonian, and in the second slot, for example, the qi coordinates, then what remains from this expression will be just one partial derivative of h, will be this partial derivative. So we get the right-hand side of this q dot equation, we get by bracketing the Hamiltonian with this coordinate. And the same for the momenta, we get the time derivative of a momentum by bracketing the Hamilton function with this momentum coordinate. And in fact, using the chain rule, this applies to any function of positions on momenta. Any time derivative of such a function f will be given by the bracket of the Hamilton function and this function f. And there are some couple of consequences you could take from this, but most importantly, from this last one, we see that f is a conserved quantity, so f doesn't change in time if and only if its bracket with the Hamiltonian is 0. So conserved quantities of a Hamiltonian systems are those functions that have 0 Poisson bracket with the Hamiltonian function. And the reason why I emphasize this Poisson bracket description is that this is the core of the most famous, one of the more basic notions of integrability, one that you would find in any textbook on the topic. And this is known as Liouville integrability, or also Liouville-Arnauld integrability. And it's very much in the spirit of what I had on the first slide, or well, one of the first slides. A Hamiltonian system is integrable if it is part of a sufficiently large family of compatible equations. So here on the Hamiltonian side, this means that the system with Hamiltonian H is integrable if it is part of a family of n Hamilton functions. So H is H1, and then there's an H2, H3 through Hn. And the compatibility condition is that between each pair of them, the Poisson bracket is 0. And you'll notice that in this condition, H1, the original Hamiltonian, does not play any special role. Mathematically, all of these Hi are on the same footing. So each of them could define its own dynamical system. Physically, we might be interested in only one, but mathematically, they all define its own dynamical system. And because of their Poisson bracket vanishes, each of these functions is also a conserved quantity for all of these systems. So these combined dynamics of these n systems, they will stay on a level set, combined level set of all of these Hamilton functions. So instead of being in two n dimensions, we are then on a submanifold of this R2n that is only n dimensional. And if some compactness condition is satisfied, then it can be proven that this is always an n-dimensional torus. And this can be a bit abstract. So we're dealing with quite high dimensions here, but you can see this in some example. So for example, think of a central force in the plane. So we have two position coordinates, which we plot here, and two momentum coordinates as well, which we don't show in the picture. But so n would be 2 here, so we'd be working in R4. And this is almost an inverse square force that I'm showing you here, but not quite. So it looks like it will be an ellipse, but it doesn't close. Instead, it will have a bit of precession. This ellipse rotates around. And if we run this for a long time, it will complete a full circle. And this almost looks like a 3D picture now. We see a projection of this torus that lives in the 4-dimensional space, two position coordinates, two momentum coordinates. We project it down onto the position planes, and we see an image of this torus from integrable systems theory. So this is physically not always the most important aspect of integrability, but it's a very nice mathematical theorem, and in some cases, we do see a nice visualization. What may be more relevant to actual calculations is that on this abstract torus, we can find a change of variables called action angle variables that makes the evolution linear. And this is, again, I'm hiding all the proofs here. This is a non-trivial statement. But as a consequence of this condition, we find a change of variables that makes things linear. And this should be a bit of an aha moment. Going back to the beginning, integrable systems are nonlinear systems that behave as if they are linear. And in this case, and in many types of integrability, we can actually do some kind of a change of variables, a very complicated change of variables that reveals an underlying linear system, which then explains this nice behavior. So we have a lot of very nice properties coming out of this notion of Liouville integrability, the vanishing of the Poisson bracket. But for the rest of my talk, the most important bit will be that the flows commute. So if this phi is the flow over time t of the system with hi, and the other one is the flow over time s with the system of hj, then it doesn't matter if we first run the system j for time s and then the system I for time t, or the other way around, we'll end up in the same place. And this might not be obvious just from what I mean by that description. And I want to set a stage for the next section of my talk, so let me spend another slide on this notion of commuting flows. Let's consider just the simplest case where we only have two Hamilton functions with vanishing Poisson brackets. So each of these Hamilton functions defines a dynamical system. So my z here is just a shorthand for positions and momenta. And we can write the time derivative of any function of these coordinate z as the bracket of the function with the Hamiltonian, or the other way around, or we would get a minus sign. So we do this for h1 and name the time variable t1. And when we do it for the second system, h2, we give the time variable a different name, t2. And the commutativity of these flows means exactly that we can think of z not just as a function of a time line, but as a function of a time plane spanned by t1 and t2. And if we move in the horizontal t1 direction, we use the first differential equation. If we move in the vertical, the t2 direction, we use the second differential equation. And if you put some initial condition at the origin, it doesn't matter if you go to your point of interest first horizontally, then vertically, or the other way around, you will end up with the same value for your point of interest. Or you can also take some other curve through multi-time. You will always have the same answer for what z at t1, t2 is. And so this time plane, or in general, this Euclidean space of several times, we call this multi-time. And because of the commutativity, we can think of solutions as having our functions not of a timeline, but of multi-time. So I've promised in the title of my talk that I would talk about variational principles. So I've given you one slide on Hamiltonian mechanics. Let's also give you one slide on Lagrangian mechanics. Again, you have here one function that gives you the dynamics. This is now a function on the tangent bundle, which you can still think of as r to n, but now the coordinates will be positions and velocities rather than momentum. And we look for curves, we look for solutions that minimize, or at least are critical points of the action being the integral over a fixed time interval of this Lagrange function evaluated on your curve Q. And you do this with fixed boundary values of the curve at the endpoints of your interval. And then minimizers, or critical points in general, satisfy this Euler-Lagrange equation. So your variational principle, you minimize something. So if you vary it, it will get bigger, or rather, if you take an infinitesimal variation, it will not change. That's the variational principle. Gives you a differential equation again. So this is an indirect way of looking at differential equations. And let me also quickly rederive this Euler-Lagrange equation. It's probably something you've seen before, and if not, it will go quite quickly. But we will do something very similar in a few slides, so it's worth looking at what happens here. So what we want to do is we take an infinitesimal variation of this action integral, which is kind of like taking the derivative of a function. And so if you look for the minimum of a function, you look for the places where the derivative is 0. Similarly, we look for curves such that this infinitesimal variation of the action will be 0. And we assume everything is nicely behaved, so you can put the variation inside the integral and use the chain rule to write it like this. So now we have one term with the variation of q and one term with the variation of qt, which denotes the time derivative of q. And this is a bit awkward, so we want to get rid of this time derivative on the variation. To do this, we do integration by parts. So instead, we get a minus sign and a derivative on this partial derivative. So we get this expression, which is the Euler-Lagrange equation, times the variation of q plus a boundary term, but the boundary term will vanish because we assume fixed boundary conditions. And since this should be 0 for arbitrary variations, this shows that your action is critical if and only if this expression is 0, meaning if and only if the Euler-Lagrange equation is satisfied. So you might know from mechanics that pretty much always when you have a Hamiltonian description, you have a Lagrangian description. And there is if some non-degeneracy conditions are satisfied, there is a quite simple transformation, the Legendre transform, that takes you from one to the other. And strangely, in the literature on integrable systems, you almost never see Lagrangian formulations. So on the Hamiltonian side, we knew that commutativity is implied, and even more than that, we had this compatibility condition by vanishing of Poisson brackets. So what is the Lagrangian side of this kind of idea? Now, suppose we can write down through standard techniques in mechanics. Suppose we can write down for each Hamiltonian function, we can write down Lagrange function. So suppose we know this Li individually, so we could write a variational principle for each individual equation, but what is their compatibility? And to a large extent, I want to argue this is captured by the strange variational principle that is in this box. And it goes by two names a bit, Puri-Lagrangian or Lagrangian multiform. And the basic idea is that you don't just take these Li, these Lagrange functions, as individuals, but you combine them into one object called the differential one form. The only thing you need to know about differential geometry now, at this point is that a one form is something you can integrate along curves. If you're not familiar about one forms, just remember that you can integrate them along curves, and apart from that, it's just something of the form Li dti, where this coefficient Li in our case are given by the Lagrange functions. And we look for dynamical variables now in the multi-time setting, so not functions of one-time variables, but functions of multi-time, of t1 through tn. And then we require that the action integral should be critical no matter which curve of integration we choose. So we could take any curve in multi-time. So here it's again just depicted as two-dimensional, but it could be higher dimensional. We can take any curve there, integrate this one form, and then we require that this action integral must be critical in the same sense as in Lagrangian mechanics. And first, when coming up with something like that, we should do a sanity check. Can we recover something that we know from this? And yes, we can. If we take as our curve a horizontal line, so in the t1 direction, if you integrate the one form like this in the t1 direction, it will only see the dt1 term. And it will just be the integral as we know it of L1 dt1. So this would just become the action integral of this one Lagrange function. So from that, we would recover the Euler-Lagrange equations of this one Lagrange function, which is what we want to be part of our system. Similarly, if we take a vertical line, if we take it in the t2 direction, we recover the usual action of L2. So in this strange variational principle, this multiform principle or Puri-Lagrange principle, we have something that contains the individual variational principles of each Lagrange function, but it has more. You can take any other curve that is not in a coordinate direction. And it turns out that if you look at the Euler-Lagrange equations that come out of this, you will get a picture that corresponds to our observation, because we will get the usual Euler-Lagrange equations in two flavors, because to get interesting examples, we should, as a minimal case, take that L1 is of typical mechanical form, so depending on positions and velocities, the T1 here is the T1 derivative, and Li we take depending on positions as well on velocities, but both in the sense of the Ti derivatives and T1 derivatives. So we will always have the usual Euler-Lagrange equation where Ti plays the role of the time variable for Li, but then we kind of have a second type of Euler-Lagrange equations, which is still of the same form, but instead of doing it with respect to Q, we take this expression with respect to T1, to kind of the alien derivative, the derivative that doesn't really belong in L1. And in most cases, this just means that the first term here will be 0, because here we assume that the Lagrangians only have dependence on first derivatives. So this second term of the Euler-Lagrange equation would then have a second derivative of Q, so that would vanish. So the second type looks a bit new, but I've written this, it like this with the vanishing term included to show you that it's still of the same form as a traditional Euler-Lagrange equation. It's the third one that's really new, and that starts capturing the compatibility of these Lagrangians. You get an equality between Li with respect to the Ti derivative and Lj with respect to the Tj derivative. You can think of this as the momenta of both Lagrangians must be the same thing. Now this is very abstract, so let's rush back and bring this to a more concrete setting. Let's consider the Kepler problem. So I briefly showed you a central force problem before, which was very close but not quite the Kepler problem. Now we actually look at the Kepler problem, so inverse square forces, which has an inverse distance potential. So we can take this as our L1. This is the physical Lagrangian if the mass is equal to 1 at least. And we combine this with an L2, which is a bit of a weird form, but this is chosen such that things work. So to motivate the choice, let's just see what comes out of the Euler-Lagrange equations of these two Lagrangians combined into a one form. We get the usual Euler-Lagrange equation of L1, which gives us the second derivative equal to a minus inverse square force. So this is the gravitational force. This gives us the motion of a Kepler orbit. And then we have the usual Euler-Lagrange equation for L2, which gives us something that is a bit ugly. We get a mixed T1 and T2 derivative. So let's forget about that for now, and let's see what the rest brings us. So the next one is this Euler-Lagrange equation of L, but with respect to Qt1, which is really just the partial derivative of L2 with respect to Qt1. And this gives us a very clean equation. It gives us the T2 derivative is equal to a cross product between Q and this fixed vector E that we put into the Lagrangian. So a time derivative equal to a cross between a fixed vector and your position gives you a rotation around this fixed vector. So this makes it clear that this Lagrangian one form here describes the physical motion and a rotation. And once we have this equation, we can look back at the second equation and see that it is just the T1 derivative of this rotation equation. So this second equation isn't really relevant, it's a consequence of the third one. And then the final equation, the compatibility condition, may be a bit disappointing because it just says the T1 derivative is equal to the T1 derivative, which is a bit boring, but it just means that our compatibility condition has been satisfied by the choice of L2. And this is the reason that we chose this first term in L2, a product of a T1 derivative and a T2 derivative. This choice of kind of kinetic term for L2 makes sure that the compatibility condition here is satisfied. And well, this one form in two time variables captures just one symmetry. The Kepler problem actually has more symmetries that you could capture. It's integrable and in fact super integrable. But as a basic example, I think it's sufficient to just capture this one rotation. Now, I want to tell you a brief word about how we actually obtained this strange new Euler-Lagrange equation from this multiform variational principle. So the variational principle was that the action integral had to be critical on every possible curve in multitime. And well, that's a lot of curves. So the first thing we want to try to do is narrow down the sets of curves we actually need to look at. And there's this very nice approximation argument you can do. You can approximate any given smooth curve by a staircase like this, a stepped curve that is only straight pieces in coordinate directions. And you can show that if you make this approximation finer, then also their integrals along the smooth curve and the stepped curve will approximate each other. So it's sufficient to only look at these stepped kind of curves. And the next simplification comes from the fact that variations are really a local thing. If we have a variation with a large support, we can always split it up into variations with very small supports and look at them individually. So it's sufficient to look at one little section of the stepped curve, so at one corner of the curve. So let's look at such a corner. It has straight parts Si and Sj and a corner point C. So let's look at the part Si, for example. And we try to do the calculus of variations as we did it before, as they do it in any Lagrangian textbook. And so we pass through this variation through the L, but now Li could depend on q on qt1 and on qti. So we get this additional term here, but apart from that, nothing has changed. And now we would like to get rid of the derivatives on this variation delta q. Unfortunately, we're only integrating with respect to dti, so we can only integrate by parts with respect to dti. So we can get rid of this term and put it in here by integration by parts. But this one, with the t1 derivative, we just have to leave b. And then integration by parts gives us a boundary term at c. But now c, it's the end of our straight piece, but it's still an interior point of our curve as a whole. So we cannot now say that variations must be 0 at c, so we have to keep track of the boundary term as well. And this was for the point S, for the piece Si. For the other piece Sj, you would get a similar expression. So if you then put everything together, we see, well, in here, we see the usual Euler-Lagrange expression, which gives us the first kind of multi-time Euler-Lagrange equation, the usual Euler-Lagrange equation. Now we see that from this delta qt1, which we couldn't get rid of, this is what gives us the second type of Euler-Lagrange equation, which, if you allow general dependence on higher derivatives, would still be an Euler-Lagrange expression just with respect to t1 instead of q itself. And the real new one, the third type of Euler-Lagrange equation, it comes from this corner condition. So where the two straight pieces meet, each of them gives a boundary contribution with a delta q, which must be set, which must be 0. So both contributions must match for every delta q, which gives us that these two partial derivatives, one of Li and one of Lj, must be equal. And this is how this variational principle in multi-time gives us a compatibility condition between Lagrangians. We can do, as I mentioned, the same kind of thing for a higher order Lagrangians. In the interest of time, I won't say too much about it. If you're familiar with this expression of a variational derivative, you can write things very compactly as two types of equations, one that are traditional or Lagrange equations and one that are these additional corner conditions. In my introduction, I talked about PDEs, and so far everything I said was about mechanics, ODEs, but I want to very briefly talk about PDEs because everything works in the same way, or almost everything. If we think about something like a wave equation, like a Korteweg de Vries equation, that involves a space derivative and a time derivative, the usual Lagrangian formulation would be an action integral over a space-time plane. So now our integrals are two-dimensional, so to generalize it, instead of one forms, we will use two forms. But apart from that, the idea is the same. Given a two form like this, we can integrate two forms along any surface, and this is what we require. No matter which surface we choose, we should always have a critical action integral over this surface. And this gives us very similar Euler-Lagrange equations. You have one type of equation that is the traditional Euler-Lagrange equations that comes from flat pieces of the surface, so to say. You have one that involves two of the coefficients of these two forms, two Lagrange functions, if you will, coming from the edges where flat pieces meet. And now, if you look at the corner of the cube, you have flat pieces, edges, and the corner point. And in the two-form case, from the corner point, we would get a third type of Euler-Lagrange equations involving three of these variational derivatives. So each time you go up a dimension, you will get a new kind of Euler-Lagrange equation, but the way you get them will be always very similar. And let's briefly look at one example, at the Korteweg de Vries hierarchy, which is the first equation of this is what described this wave in the video I showed you at the very beginning in the narrow and shallow canal. And it's part of an infinite hierarchy, actually, but here I just write the next member. And the x will be the space coordinates, but in this multi-time setting, I was only using t's, so t1 will be our x. And then there are Lagrange functions known for these two equations, or almost, because the Euler-Lagrange equations of these Lagrange functions will only give you a differentiated form. So they will give you a mixed space-time derivative equal to something rather than the time derivative explicitly equal to something. But if we put this into our multiform formalism, well, we want to have a two-form in 3 dimensions with these two coefficients. So L12 is the coefficient of dt1, dt2, L13 the coefficient of dt1, dt3. But then there's a third coefficient that makes up a two-form. So we should find a suitable L23. And I don't really have time to get into what suitable means, but it's a kind of non-trivial exercise. And the fact that we can find it is closely related to the fact that the system is integrable. But what I do want to point out is that once we have found a suitable L23, so once we have this two-form, then we see something very nice. As the multi-time Euler-Lagrange equations, we get the usual Euler-Lagrange equations, which I mentioned are only the differentiated form of the equations we're actually interested in. But from some of these new Euler-Lagrange equations, in this case, the ones involving 2 of the Lagrange functions, we get the same equations, but in their evolutionary form. So the stronger version that explicitly says your time derivative is equal to this. So the multiform here gives you the equations in a more explicit, in a stronger form than the individual Lagrangians for the equations could ever. So besides any integrability theorems, this gives you already a very strong impression that it is a good formalism to capture these kind of equations. Now, we should come to an end fairly soon, but I want to say a brief few words about some connections to the textbook world of integrability and maybe a few sentences about how to generalize this to other contexts. A very important aspect that I haven't mentioned and that will allow us to make these connections is a second concept we need from differential geometry, which is the exterior derivative. If you don't know it, just think of it as something that has coefficients of this form. So the L2 component differentiated with T1 minus the L1 component differentiated by T2. And it turns out that on our Kepler example or on any other reasonable example, that this expression always takes a nice form. It factorizes into a product of 2 terms that vanish on the equations of motion. So on the equations of motions, this exterior derivative will be 0, and in this sense, it will even attain a double 0. And I'm presenting this as an observation. It's almost a theorem. And if you make your definition of the variational principle slightly stronger, it is a theorem. What it means geometrically is that the action, which we said must be critical on every path through multitime, also does not depend on which path you take. And this is a consequence by Stokes' theorem of dl being 0, that both paths you could consider, or all paths you could consider, have the same action integral. So this closeness condition, meaning dl equal to 0, is something that has a nice geometric meaning. And it is what allows us to connect this to the picture I had at the very beginning. So I formulated, as do textbooks, integrability in terms of Hamiltonian mechanics. And I mentioned that with some mild non-degeneracy condition, you can, on the level of individual Hamilton functions, transfer between a Hamilton function and a Lagrange function on the other way around. And similarly, we can do this from in the one form or the two form perspective. We can associate each Li to an Hi or the other way around. And on the Hamiltonian side, what gave us integrability, what was the definition of integrability, was that the Poisson brackets of pairs of Hamilton function vanish. And what you can show by calculation, basically, if you have this transformation between Lagrangian and Hamiltonian formalisms, is that this Poisson bracket on the Hamiltonian side is given by this expression on the Lagrangian side. And this expression was exactly the same as what we had on the previous slide. It is a coefficient of this exterior derivative dl. So dl is 0 if and only if the Poisson bracket is 0. So in addition to the variational principle, as I presented it in most of my talk, this dl will give us the final ingredient. dl being equal to 0 gives us the final integrability ingredient and establishes equivalence to the Hamiltonian side. And you can do a similar thing for 2 forms or higher forms when you're dealing with PDEs, although it's a lot more messy because Hamiltonian structures are a bit more complicated, and the equivalence becomes a one-way implication. But still, there is a very clear connection between the exterior derivative of L being 0 in the Lagrangian multiform picture and Hamiltonians being an involution. In a similar sense, the L being 0 expresses that the flows are variational derivatives of each other. And a variational derivative means that you change your Lagrangian by a constant, and if you change Lagrangian by a constant, it doesn't affect the equation of motion. And you can check that this dl being 0, so these 2 derivatives being equal, exactly means that the tj evolution changes lk by tk derivative, and changing lk by tk derivative will change the action by a constant, so will not affect the equation of motion. So in this variational sense, they are symmetries of each other, which goes back to my very first part. An integrable system is a system with many symmetries. And maybe this slide, in the sense of time, I should skip, but you can even move this beyond integrability. If you have symmetries that do not all commute with each other, you can still fit it into the framework, only instead of multitime being a Euclidean space, you would take a Lie group as multitime. But this is more recent work and quite subtle, so I will not bother you with that too much at the end of my talk. The final thing I want to mention is that you can apply exactly the same ideas, and exactly they originated there in the discrete setting. So you can do this for lattice equations. So for example, where it started is in quad equations, where you have equations involving functions on 4 corners of a square, but no derivatives, only shifts in the lattice to the next square. And then in a very similar way, you can think of your lattice as part of a higher dimensional lattice, look at surfaces in this higher dimensional lattice, and integrate a Lagrangian, which would then be a sum of Lagrangians over this lattice, or the surface in the lattice, and require that the action should be critical for all those lattices. And you can do the same if some of it is discrete and some of it is continuous, like the Toda lattice. If you have heard of this example, you have a discrete space but continuous time evolution. There you can also apply the same ideas. So to summarize, after giving you an introduction to integrable systems, I have talked about the flavor of integrability that I've worked on, which is this Lagrangian multiform or pluri-Lagrangian principle. It gives us a variational principle for integrability, and the beauty of it is it applies very widely. It applies to ODEs, to PDEs, and discrete as well as continuous, as I mentioned at the end. And the ingredient that connects this to many more famous topics in integrable systems is this closeness condition, the fact that the exterior derivative of this Lagrangian form is 0. And this also gives us ways, these connections also give us ways to construct Lagrangian multiforms. There are still a lot of open questions. A few of these things I mentioned are quite recent work. They're not quite developed yet. Also, using these ideas to construct explicit solutions is something that's still a bit up in the air. And everything I've talked about is classical. I know that our host is also very interested in the quantum side of these things. So I hope in the future we can say more about that. I'll leave you on my last slides with a few references, some textbooks that I would recommend if you want to learn more about integrable systems in general, and then a very biased selection of papers on Lagrangian multiforms if you want to start reading about those. But as I mentioned, there are many other works of those, including some by our host today. So talk to him as well if you're interested about these kind of things. For now, I'd like to thank you very much for your attention.
All right. Well, thank you very much, Matt. Well, for this kind of very wonderful introduction to this volitional principle. Well, for integrable system, very. Well, I think it's very nice, and it would be a good material for students who are interested in this kind of business to start with. Well, if they want to get into this, yeah, this kind of doing this research, right? Anyway, well, well, I really love the way that you give the overview at the beginning about the integrable system, right? And then you mentioned about nonlinear equation, which it actually might behave like a chaotic something like that. But I believe that actually the chaos and the chaotic system and integrable system are totally different, right? But they're
Yes,
both non-linear, right?
yes, they're the opposite end of a spectrum in some sense.
Mhm.
You can have systems with some structure, but not quite enough to be integrable. They would fall kind of between. But if you see a nonlinear equation, it's quite reasonable. If you don't know anything about it, it's quite reasonable to expect at least a little bit of chaos. Maybe
Okay.
there are places where the solutions will be well behaved, but if you see a nonlinear equation, the expectation is that the behavior will be complicated. And it's only when you discover, oh, it's integrable because it has all of these symmetries or because it has this other type of structure, it's only then that you can have confidence that you can really understand the equation and its solutions to the fullest.
All right. Okay. Actually, I love the way that you put in your note. Actually, for the integrable system, we should actually nonlinear with a nice behave or underlying structure, like something like that. If I remember correctly from your slide, then
Yes.
yeah, then I would say that for the chaos system, well, for the chaos system, this would be not nice, right? Nonlinear with a not nice underlies somehow. Well, we cannot control it somehow in some sense, right?
Yes, and in I guess it depends on your perspective and what you think of as the normal case.
Mhm.
But I think most systems coming from the real world, most systems are not integrable. They may
Yes.
be close to integrable, so then you could still use integrability theory through perturbation methods, but
Yeah.
most systems will not be integrable.
Yeah.
So in my mind, integrability is the exception. Most systems are not nice. Of
Yes.
course, there's a lot of fun things you
Yes.
can do with those systems as well, and interesting mathematics going on. But from the perspective of solving things, most systems are not nice, and integrable systems are the good behaved, the well-behaved, nice exception.
Yeah. Right. Yeah. 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 Okay. That is a thing. Yes. Okay. Well. And then when you mention about Liu will integrability. Yeah. Yeah. And then you put like a key message that actually we have like nonlinear right behavior, but actually somehow when we get a set of action angle variable that actually not that we already turn somehow from the nonlinear thing to be in linear thing, right? That is a nice message here, I think. Well, that is the reason why we can solve for the solution somehow. Is that right?
Yes. So in some cases there may be other routes to a solution, but yes, I think it's fair to say that the reason you can find a solution, and in many cases the way you would find a solution, is to find this change of variables that linearizes it.
Yeah. Yeah.
And the same is true for the PDEs, where we see this soliton solution for KDV, or the multi-soliton solutions. So this multi-soliton solution like this, there is also a linearizing change of variables, because in the background here, it's much more complicated because we're dealing with a PDE, but really there is a change of variables in which all of this behaves linear, and this is known as the inverse scattering transform. So yes, in many instances of integrable systems, it is possible to find this linearizing transformation of variables, which is why we can solve it.
Yes, indeed. And I really like your example here. Actually, at the end, you get like a projection of the torus on the 2D plane. Very nice example. Yeah, very lovely picture there. Yeah.
Yes, it's something I only realized after doing this for many years, that it's actually quite easy to get this visualization.
Yeah, because somehow, most of the system is very difficult to visualize, right?
Yeah.
Yeah, then this is a very nice one of the nice example, I think. Yeah.
And the way you do this, if anyone wants to try making such a picture, you take the Kepler force, so inverse square, and then add some kind of perturbation, maybe fourth order with a small parameter, and this small perturbation will cause this precession in the orbit, and then if you run it the appropriate time, you will get a very similar picture. So it's quite easy to implement if anyone wants to do that as an exercise.
All right. Okay. Can I ask you about your lemma at the very end that you put the lemma here. Well,
Yes.
on the left-hand side is the Cauchy relation, I believe. Right, yeah. And the right-hand side is the Hamiltonian commuting flow. The way that you put the equal sign here, you mean that actually these two, these two quantities are equivalent, right? So, in some sense, right?
So, if you are in a setup where you can do a multi-time Legendre transform,
okay.
So you have an explicit formula relating your LJ with your HJ in that setting.
Right. Yes. Yeah.
So say you are given your Hamiltonians, you use this formula to write down your Lagrangians, you evaluate this, any time derivatives that are still in there, you use the Euler-Lagrange equations to plug in, and then you will get exactly the same expression on the left and on the right.
Okay, I get your point now. Yeah.
And that, of course, implies that if one is 0, the other must be 0 as well.
Yeah, sure. Yeah. We would expect that. Yeah, this whole relation must simultaneously holds, right, for the integrable system. Yeah. All right. Very interesting. Yeah. All right. And then, actually, for I would say for the big picture, that actually on one side we have like a Hamiltonian setup, and then we can define the notion of integrability, right, through the like a Liu view, and then you can capture the compatibility that you mentioned through this quantity, the Poisson bracket here, right? And then on the other side we have Lagrangian setup, and then we do the variational principle, and then we ended up with the Cauchy relation, which is give us again the compatibility in some sense, I would say, right? And then they are both equivalent. Is it correct?
Yes, as a big picture, it's correct.
Yeah.
It comes with a little bit of a caveat that you need some kind of non-degeneracy condition for them to be equivalent. Yeah. So there might be systems for which you can write down one but not the other. And I'm not sure that will happen in the ODE case. But if you think more towards the discrete world, then it's much more difficult to formulate the Hamiltonian side. But the variational principle works in exactly the same way, or in a very similar way.
Right.
So the Lagrangian side, I think, gives us the possibility to connect these ideas to different settings where the Hamiltonian formulation becomes unclear or even non-existent.
I see your point. Yeah, right. Yeah. Is you mean that at some situation this the Lagrangian setup might offer a nice way to study the system, right?
Yes.
Yeah.
And in some other cases the Hamiltonian will be better. I'm not claiming Lagrangian is always better, but there are places where it will be useful.
yeah, of course. It depends on what kind of system that actually you're looking at, like, yeah. All right, okay. So, well, then at you also show some open problem that actually, well, yeah, that's open question that still need to be, yeah, settled. A lot of them, I believe, yeah, yeah. And then I hope that, well, for students who are interested in this kind of business, might need to, well, if you want to do something on this integrable system business, like this or the list that actually Matt put here might be, yeah, yeah, your future research, I would say, topic. And if you for well, if you are interested, well, you might probably contact Matt personally, I think.
Yes, feel free to get in touch.
Yeah,
And yeah, if you're local, you can talk to
yeah,
him as well.
yeah, sure, of course.
Just feel free
Um,
to get in touch with me.
yeah, okay. So I'm not sure whether there are some questions from the online audience or not. I don't see it yet, but well, but I don't. I guess there is no question. Um, anyway, so if there's no question from the online, then I think, well, we spend, well, about hour, roughly speaking, for this um, activity already. Then, well, I would say, well, I would like to thank you again, Matt, for this wonderful talk. I would say, and
You're welcome.
and
Thanks for having me.
yeah, and thank you for everyone who oh, okay, actually, there is a question here. Can you see the question?
Yes.
In the lemma on page 20, I have seen that there is factor 2 at left hand side.
It's it probably depends on how exactly you write down the Legendre transform, because if you multiply all of your Hamiltonians by 2, you get a completely equivalent system, and then you would have the factor 2 in that expression. So if you rescale all of your Lagrangians at the same time, or all of your Hamiltonians at the same time, you get a completely equivalent system, but you could get a factor in that kind of relation.
So this factor is just a matter of scaling. Is that your answer, right?
Yes, I would think so.
Okay. Well, I don't want to say thank you again, but yes, yeah, thank you again, Matt, for this nice talk. And before we go, for the online audience, you please help us to complete the form, and then we can get all the feedback, and then we can improve our activity next time. And then, well, you can actually, well, it's about then, yeah. See you again in the next if Colloquium number 11 next month, and stay tuned then, and then you can follow, well, our activity on the Facebook page of the institute. And for today activity, thank you very much, and bye bye.